So my name is Christou. I'm an associate professor at the American College of Greece, together with Nikos Bakas, from NCC Greece. And I will present research work that we did for ESA last year between late 2023 and October of 24 on developing LLMs for satellite communication knowledge management for the European Space Agency. And of course, this is joint work with Alessandro Mocho, Sergio Rojas, Francisco Valverde from the University of Malaga at Spain, Dimitris Voyagis, a colleague of ours at ACG, and Thomas Navarro at the ESA. So I will give you an overview of the problem and some related work. Then I will describe the knowledge extraction process, which, as you shall see, has a lot in common with what Luca and Andrea already presented. And then I will, instead of discussing a RAG process, I will discuss a fine-tuning process that we followed so as to have an on-premise model that can act at the same level of accuracy as the large public models, at least, let's say, ChatGPT 3.5 or maybe 4. I will finish with an evaluation of the fine-tuning models that we created, results, and then some key takeaways and future directions. So, as the previous speakers very nicely put it, applying large language models to niche fields is something very important, has many benefits. It also presents unique challenges. One can easily see that even the largest trillion parameter models that we see today from ChatGPT 4 or 5 or the Gemini models, still they are not performing at the expert level in certain fields for which there are not many related data in their training set, or if they have not been fine-tuned via HFRL in their post-training phase. Satellite communication in particular encompasses a wide range of technical detail protocols and operational guidelines that a model needs to be, a large language model that is, needs to be trained on specifically in order to produce good results in practice. For reasons of privacy and data security, which were major requirements in this particular call for projects that we responded to from the ESA, it was the SatNex 5 project, we are only investigating on-premise models and their performance. So, we have worked with two major models that were already, well, one of them was mostly mentioned in the previous talk. It was a Llama Instruct model version 3 with 8 billion parameters, as well as the Mistral Instruct model, 7 billion parameters. Now, these models, of course, need some server to be embedded with so that they can then respond to user queries via some protocol like HTTP, etc. So there are a number of on-premise deployment tools like Ollama, the Anything LLM server. Of course, the VLLM server that a couple of years ago was touted as a very nice server that could speed up operations even concurrent requests on the same server and the same model. And of course, the LM Studio, which offers a kind of an integrated development environment, together, of course, with an embedded server to which once you have loaded up a model, it can be used to serve the model inference. So you can see here on this on this table that I'm showing you how the various tools and the various servers feature in terms of platform purpose, model support, user interface capabilities, deployment options for various LLMs, integration features, security and privacy features, and finally, how much scalable each solution is. At the beginning, we started with LM Studio because it was quite easy to work with. Eventually, we switched to Ollama and anything LLM. For VLLM, for the particular hardware that we had available, we found it back then, at least last year, it was relatively unstable for anything other than very small size models. So we did not end up using it. Now, the knowledge extraction process is very much the same whether you are doing retrieval augmented generation or fine-tuning, especially when you have to work with large PDF documents. The key challenges in PDF content extraction is about the nonlinear layouts of PDF pages, mixed content types used within a single document, header, footer, noise in those areas, and of course the non-textual elements that might be included, which of course make absolute sense from a visual perspective to humans, but they make the work of extraction tools much harder. We ended up coming up with a cleaning pipeline that involved text extraction using any of the tools that you see at the top right of this slide, removal of irrelevant content, deduplication of content that may appear more than once or may be very, very similar. For example, in a legend of an image, of a figure or a table, taking care of ethical considerations, even though in this particular project that we were, where all the documents were taken directly from the ESA website, so there wasn't any content that could be considered offensive to certain groups of people or to ethical values, etc. And then finally, we follow the normalization procedure to create the final content. Table handling is always an issue in document extraction, in knowledge extraction from documents, whether it is PDFs or if it is pure text, right? Here, the table handling was an absolute necessity because there are many issues to be found, as we discovered when we are trying to extract knowledge from the PDF documents of the ESA. We found one particular tool, Camelot, to outperform both Tabula as well as Acrobat in this process. And this is why, we used it to do most of the table handling. Improvements we were able to obtain included filtering out tables in headers and footers, as well as eliminating any overlapping text fragments within the documents or the cells in the documents. Next comes the fine-tuning phase, where the data set that we have obtained is used to actually change the parameters, as the previous speaker said, of the LLM. For doing this, we used low rank adaptation, so as not to have to spend too much time changing all the parameters of these 7 or 8 billion parameter models. And we also used the SFT trainer model from Hugging Face. After that, we perform model merging and quantization, of course, because even though we actually ended up with one particular model that we did not quantize at all, but we kept the full model and all the accuracy that we had for every parameter. And the final step is to prepare the conversion of the parameter files to a GGAF model file, so as to be able to give it to the servers that we mentioned before to serve the model directly, for example, via LM Studio or anything LLM and the rest, right? Now, you can see the single machine that we used to do this fine tuning on the lower left of the slide. It is a Linux server that we are full administrators of it. We installed directly on the Iron Ubuntu Linux 22.04, the long-term support release. The machine has one AMD EPIC CPU with 32 cores running at almost 4 gigahertz. It also has a single NVIDIA L40 GPU with 48 gigabyte of video RAM, which turned out to be enough to do the fine-tuning that we wanted in approximately 8 hours. We provided a cutoff time of 8 hours for each of our fine-tuning runs to see how the models actually perform after this relatively small runtime in a low-end server. By the way, this server is a micro server. I forget the name of the company that makes these servers, but I do remember the cost. It cost together with VAT. It was a 15,000 euro machine. So it's a rather cheap machine, which is of course extendable. It can get another three GPUs. And one more same AMD EPIC Genoa CPU. The total RAM memory can be expanded to like 2 terabytes, and there are enough slots for SSDs, of course. So basically, the fine-tuning process took place on our data set, which comprises of approximately, if I remember correctly, 5 gigabytes of text extracted from the documents, from the publicly available PDFs of the ESA website. And we also developed, with the help of one of our students at the American College of Greece, Mr. Hastoukis, we developed a web app in order to facilitate with user-to-model interaction. So besides the server, the Olama or the LM Studio or the anything LLM server that actually serves the model, we have a web server that is based on the Django framework, Python framework for developing web apps, which actually serves web pages to the browser of a user, who can then in turn actually send directly queries to the web app, and the web app sends these queries to the model server, gets back gets back the responses, and serves them back to the user. The web app also has the ability to perform RAG if needed, even though we didn't do anything like that, and has a number of other capabilities. Here you can just see a couple of screenshots that showcase some of the functionalities of our web app. The major functionalities is to register users, to manage them, to communicate, of course, with the server hosting the large language model. We have the ability to swap LLM servers at the runtime. If the user doesn't like a response from one model, they can swap to another model if we had one. And a corresponding server. It manages user chat history, and it allows for RAG operations, as I already mentioned. The overall process workflow looks like this data flow diagram that you see on the right of this slide. So from the original data set of PDF that we scraped from the ESA website, we perform text extraction as well as table content extraction via the use of the Camelot framework. This follows the preprocessing phase. This is fed as input to the preprocessing phase that I mentioned. And then we actually went ahead and tried two different approaches to fine-tuning. The first was to provide the data set, this extracted text as it was, as input to the fine-tuning process. So essentially provide it as essentially document completion, right, to the LoRa. And the second was to first create question-answer pairs, which could allow the data set that is given as fine-tuning material to the LoRa process, much closer to the question answers that we wanted to make the system learn, right? So, whereas the first attempt just gives the entire extracted text as further training material, the second attempt actually generates a set of question-answer pairs using, in fact, a large language model, and then proceeding to the fine-tuning phase. And after that, we performed, actually our colleagues at the University of Malaga performed the evaluation phase, where we are using yet another LLM as a judge, and we compute some custom factual metrics. So the response, the results, as you can see here, are relatively, from the first attempt, are relatively disappointing in the sense that the fine-tuned models, both Llama and Mistral, actually perform slightly worse, and in fact, in some cases, quite worse than the non-fine-tuned models, right? On simple facts, on accuracy, on completeness, as well as in fact precision, the versions that were fine-tuned but without question answer, but on the straight text, perform quite worse than the non-fine-tuned models. On the other hand, when we fine-tune based on question-answer pairs that we have generated from the extracted set, then you can see that the Mistral instruct version with the 7 billion parameters actually performs 6.7% better on simple fact question answers, improves accuracy by 3.7% versus the non-fine-tuned, the base Mistral model, increases completeness by 6.5%, and increases fact precision by 4.3%, and this is just after a single 8-hour fine-tuning process. Overall, therefore, we have come up with a number of lessons learned, let's say. First of all, that the structure and format of the training data matter significantly. So once you pass into the fine-tuning process a question-answer pairs for a task that is a question-answer basically requirement, you improve dramatically on the base model. Simple domain-specific, therefore, question-answer generation with the help of another large language model proves to be a practical strategy when the original dataset is not already in a training format. Fact-based evaluation metrics tailored to specific needs provide much clearer insights than generic scores. And finally, for the future work, we could explore extended training durations. As I said, we only let every fine-tuning run only run for 8 hours. It was also summertime, and we had some issues with overheating and the like, because we actually had the server as available to us physically in our desk, right, instead of having it in a rack in the IT department premises. We could use more refined dataset generation process strategies, and of course we could try to use additional evaluation criteria to further improve performance and reliability in what appears to be a secure mission-driven setting like the ones that we have at the ESA. And with that, I'm going to finish. Thank you very much, and I would be happy to take any questions.